Welcome back. So this vignette's entitled "In the Steps of Turing," and the plan is for us to investigate a few pieces of his paper, "The Chemical Basis of Morphogenesis," that I showed you last time in the last vignette, where I introduced Turing and his work. And I need to say, I was rather passionate about Turing and his work, and I went off a bit on the subject of how many papers people write and their H indices, and I also made some remarks about the punishing rejection that Turing faced because of his private decisions about his life. And yeah, I guess maybe this is not a setting to talk about such things, but it leaves me feeling deeply upset, is the bottom line. That, a man living his life was subjected to such cruelty on the basis of something which it doesn't add up for me. I don't understand it. So he wrote this paper on the chemical basis of morphogenesis, and I already explained to you the conception, which we're going to explore here. And let me just show you that conception, and then we'll take a look at his paper. So the conception is that we have two cells, and there's two chemical species in those two cells, which we will call X and Y in imitation of Turing. And one of them is an inhibitor, and one of them is an activator. X is an activator, Y is an inhibitor. You'll see that in a few moments. They have different diffusion coefficients. And what we're going to ask is whether the homogeneous state is unstable to the development of a perturbation, which would correspond to a heterogeneous distribution of the activator and the inhibitor. So that's what we're going to do. And my plan is to basically exactly imitate what Turing has to say here. And so he says this breakdown of symmetry or homogeneity may be illustrated by the case of a pair of cells originally having the same or very nearly the same contents. The system is homogeneous. It is also symmetrical with respect to the operation of interchange in the cells. The contents of either cell will be supposed describable by giving the concentrations X and Y of two morphogens. So already, this kind of fits into our continuum theory and rate equation protocols, because the first step is that we have to decide what variables we're going to keep track of. And in this case, we're going to keep track of X of position and time, and Y of position and time. In this first case, we will call X 1 the value of X in cell 1, and X2 the value in cell 2, and etc. When we get to Turing's ring of cells in the next vignette, then we'll have to be a little bit more clever. But for the moment, that's the way we're going to do it. And in fact, my plan is to first look at the single cell case. Now, let me note something. Here he tells us about his chemistry. It's purely artificial. It's a game. It's chosen in order to have some simple properties. He says the chemical reactions will be supposed such that on balance, the first morphogen is produced at the rate 5x minus 6y plus 1. Let's read those words. It's a sentence, but it's an equation, and it's a differential equation. The first morphogen is produced at the rate 5x minus 6y plus 1. That's this. The second one is, and the second y at the rate 6x minus 7y plus 1. So that's this bit. So that's a second differential equation. That's the rate at which y is produced, and that's this equation. So we have a two differential equation system, two coupled differential equations. Note why we're inspired to call X the activator, because the presence of X increases the amount of X and Y, and the presence of Y decreases the rate of production of both X and Y. So if Y goes up, then production of both goes down. So this is very simple, and it's linear. And yeah, that's fine. When, however, the strict application of these formulae would involve the concentration of morphogen in a cell becoming negative, it is understood that it is instead destroyed only at the rate at which it is reaching that cell by diffusion. So, there's some pathologies here. And one of the most interesting things that it took me a long time to appreciate, and Erwin Frey in Munich has been saying very interesting things, and I plan on having a vignette about this, is not a mass-conserving set of reactions. If I add dx by dt plus dy by dt, I don't get 0. So x plus y is not a constant. And so what Turing is saying is, by accident, we could actually, in this artificial system, could end up with negative concentrations. Okay, so this is our simple system, and let me actually now do a little bit of analysis of this thing. So what I'm going to do is I'm going to explore the stability of this system. So the question we want to address is we want to explore the stability of this set of coupled equations of chemical dynamics. So observation number 1, test yourself. So if I give you a moment to contemplate this, my question is, what x and y leads to steady state? Or said in the jargon of dynamical systems, what choice of x and y leads to a fixed point? And what you'll see if you look at this for a moment is that if I choose x star equals y star equals 1, this is a fixed point. How do I know? Because if I plug in x equals y equals 1 up into the above equations, the first equation I get 5 minus 6 plus 1, which is 0, and in the second equation I get 6 minus 7 plus 1. Clearly, Turing contrived it this way. So he wanted us to have a situation in which we could, by inspection, just find the fixed points, which we just did. So in the spirit of what we did earlier in the term when we were thinking about the mutual repression switch, our task now is to address the stability of this system. And the way that we do that is we say, well, I want to know about x of t, which is equal to is x star plus little x of t, and y of t is equal to y star plus little y of t, where these two guys are the perturbation. They're the excursion around the fixed point. So that might be a better way to put what's in play here. This is the excursion around the fixed point. And what we want to do is we want to work out the dynamics of the excursion around the fixed point. So let's do that. So if I plug, let's take a look. If I plug these two values, plug this into that equation and plug that into that equation, what I'm going to get back is d of, let's be careful about it, d of x star plus xt, which is equal to d of little x of t by dt. The reason being that x star is a constant, the derivative of a constant is 0, and then I get 5 x star plus x of t minus 6 y star plus little y of t plus 1, but that's equal to 5 plus 5 little x of t minus 6 little y of t plus 1, but 5 minus 6 plus 1 equals 0, so I can drop this, and that. So what I'm left with, and if I make a similar analysis for the y equation, what I'm left with is d by dt of little x, little y is equal to 5 minus 6, 6 minus 7, and then x, y. So this is a matrix way of writing our two coupled differential equations, and this is our linear stability uh, analysis, although it's a little bit uninteresting in the sense that the original equations were themselves linear, so we didn't really have to do any stability analysis. Didn't say that right. We did not have to do any Taylor series to pick off the leading order terms in the perturbation. So, how do we handle a problem like this? The answer to that is just like what we did in the context of our earlier analysis of the mutual repression switch, and that is that we assert that x of t is equal to x naught e to the sigma t, y of little t is equal to y naught e to the sigma t. And so stability here all comes down to a question of whether or not sigma is greater than 0 or less than 0. If sigma is greater than 0, then that means the perturbation will increase in time. So we move away from the fixed point. On the other hand, if sigma is negative, then what that means is that the perturbation damps out over time, because in a large t limit, e to the minus a negative quantity times time is going to go to 0. So that's the concept. Now, why did I choose these functional forms? As I mentioned in a previous vignette, a piece of differential equation lore that you can go read about somewhere is that if you have linear differential equations with constant coefficients, then the solutions are going to be exponentials. And we can see this by now taking the derivatives. So dx by dt is equal to sigma x naught e to the sigma t, and d little y by dt is sigma y naught e to the sigma t. And I can now rewrite my, this might seem a little awkward, but I'm going to rewrite my equation as follows. This is going to be sigma 0, 0, sigma, and then acting on x0, y0 times e to the sigma t. That's a rewrite of the left-hand side after I took the derivative. And the right-hand side is of the form 5 minus 6, 6 minus 7, and then x naught, y naught, e to the sigma t. And so I can rewrite this then as 5 minus sigma minus 6, 6 minus 7 minus sigma, and then times x naught, y naught, and that's equal to 0. This is what's called an eigenvalue problem. And you may remember back to some sort of examples where you had two linear equations from high school or something, and you were trying to find out whether they intersected. And so here, what we're interested in finding out is we need to find a condition for a solution to exist. And the condition is that the determinant of this matrix, so I'm going to call that matrix M, equals 0, is the condition for our solution. So, the determinant is 5 minus sigma minus 7 minus sigma times plus 36 equals 0. That gives me minus 35 plus 7 sigma minus 5 sigma, and then plus sigma squared plus 36 equals 0. And thus I have sigma squared plus 2 sigma minus plus 1 equals 0. And so I can factor that as sigma plus 1 squared, I think, equals 0. And thus sigma is equal to minus 1. I hope I did that right. I haven't thought about this in quite a while, but yeah. So what do I want to say? Just bear with me for a second. Oops. I want to just look at something. Let's see here. just don't want to lead you astray. Yeah, so yeah, this perturbation decays to 0. Okay, I just wanted to confirm I didn't make any mistakes. So in this case, what we found is that the the system is stable against this perturbation. So what we want to do next is we want to do the two-cell case. So now I'm ready to tackle the two-cell case. So so what I say here is we're going to use scratch and sniff to write down the equations, and what I want to do is I basically want to write down the same chemistry. So dx1 by dt is equal to 5x1 minus 6y1 plus 1. And then I want to have diffusion from cell 2 to cell 1. So this term is a diffusion term. Why do I say that? Because note what it does. If x2 is greater than x1, that means there's more molecules in cell 2 than there are in x1, and it will lead to a positive term. It will contribute to an increase in the number of molecules in cell 1. So it's diffusive. dy1 by dt is equal to 6x1 minus 7y1 plus 1, and then plus dy, and then y2 minus y1. So that's the cell 1 equations. Now I'm going to write cell 2. So dx by dt is equal to 5x2 minus 6y2 plus 1, and then plus dx, but now x1 minus x2. Notice that this has an opposite sign to that in the first equation, or I suppose I could have written it as minus dx x2 minus x1 to make it clear that the diffusion part is conservative. If molecules leave cell 2 to go to cell 1, the total number of molecules due to that diffusion process is unchanged. And then finally, dy2 by dt is equal to 6x2 minus 7y2 plus 1 plus dy, and then y1 minus y2. So these are the 4 equations that describe the two-cell system. Let me just note that these pieces are the chemistry terms. And then, as I already noted, these pieces are the diffusive terms. And the question we are going to ask is whether or not this system is stable or unstable. And the key tuning parameter that we will exploit here is the ratio of dx to dy. In other words, the difference between the diffusion in the x species and the diffusion in the y species is what Turing discovered is the key parameter of interest. So we can make an observation about the fixed points. So observation, and the observation is that x1 star equals x2 star equals y1 star equals y2 star equals 1. That is a fixed point. If you look up above and you plug in x1 equals x2 equals y1 equals y2 equals 1, then what you'll see is clearly all of these diffusion terms vanish. And we already know from the previous one-cell case that these guys vanish. So we found the fixed point. So once again, we're going to ask the question of whether or not the fixed point is stable. Now, I think I could rewrite this. So what I want to do at the linear stability analysis is the next step. So linear stability analysis. So we consider that x1 of t is equal to x1 star plus little x1 of t, and so on. So we need to do this for all 4 of our variables. And we will plug this back into our differential equations. So this is x2 star plus x2 of t. And then finally y2 of t is y2 star plus y2, this little y2 of t. The strategy is plug into the original ODEs, and I will do one of them for you. So example, the first equation. So I have dx1 by dt, and then that's going to be 5x little x1 minus 6 little y1, and then plus dx of little x2 minus little x1. How did I do that? I simply imitated what I did in the previous case. Let's just stare at how that would go. So if I take this, oops, sorry. Ooh. If I take this thing and I plug it into this first equation, on the left-hand side, I'm just going to get a d little x1 by dt. And the 5x minus 6y1 plus 1, that thing will degenerate into nothing more than just this part. And then when I do x2 minus x1, what I'm going to get is x2 star plus little x2 minus x1 star minus little x1, but x1 star and x2 star are equal, so they drop out of the parentheses, and that's why I'm left with this thing. So I suppose we can just write by inspection the others. So the d1 dt is equal to 6x1 minus 7y1, and then plus dy y2 minus y1. And then I have dx2 by dt is 5x2 minus 6y2, and then plus dx. Now I have x1 minus x2, and finally dy2 by dt is 6x2 minus 7y2 plus dy y1 minus y2. Why am I so boring? So, you know, if I'm sitting here at my table by myself doing this, this is quite amusing, and it's fun, and it's part of the craft, and it's interesting to see, you know, it's fun to share this moment with Turing from, you know, like something like 70 years ago, where he sat there, he did a little calculation, and he did this precise calculation. You know, like if you look at his paper, and I recommend that you do, then, you know, on this page, what you're going to see at the top, these are the eigenvectors, okay? If that's overly technical and you don't know what it means, you know, go read about eigenvectors, but these are the outcome of diagonalizing the 4x4 matrix that we're about to get. And he's going to comment on the instability of this thing. So I think that that's, you know, really quite interesting. It's just cool that, you know, we have this shared language where we can do the same thing as him and we can get the same result as him. So now I'm ready to write this in matrix form. So let's do that by inspection. So I have d by dt, and then I have this vector which is 4-dimensional, and then on the right hand side we are going to write this matrix, and it's going to multiply x1 y1 x2 y2 in order to obtain, basically to write in equivalent matrix form the what we have up top here. So, you know, this is equation 1, this is equation 2, 3, and 4. And just as a reminder, in case you forgot about your matrix multiplications, equation 1 is gotten by taking this row and multiplying it by that column. So that's how I'm going to read off the matrix elements that I'm getting ready to write down. So let's see where x1 appears. It appears with a 5 here and a minus dx there. So I expect to have a 5 minus dx, and then there's a minus 6y, and then there's a dx and a 0. So those are the matrix elements of the first row. Now I'm going to do the same thing, so I get a 6 here, and then y1 appears twice here. It appears with a minus 7 minus dy. Yep. And then I have a 0, and then I have a dy. And then on the next level, I have a dx on the x1 position. I have 0 in the next position. For x2, I get 5 minus dx. And finally, for y2, I get minus 6. And the last row is going to have a 0 here. And then y1 is going to have a dy here. And then on x2, I have a 6. And then finally, I have a minus 7 minus dy. Okay. So here's this is our 4x4 system. And we once again want to know whether or not this thing is stable, so we take a trial solution. And the trial solution, because these are linear ODEs, constant coefficients, all those incantations, I know that x1 of t is equal to x10 e to the sigma t. y1 of t is y10 e to the sigma t. x2 of t is x20 e to the sigma t. And finally, y2 t is y20 e to the sigma t. So if I plug those things in, what I'm going to be left with is a big matrix. And I think I've done this calculation before, so let me just go grab that and save ourselves the trouble of okay, you see here, I don't know, let me just pause for a moment. So this is what we just derived. So you can go check it. I can't tell whether it's the same, but I think it is. Then I make this trial solution right here. I plug it in and I get this. And that leads me to this linear stability condition, which I'm going to copy from here and bring it over to my other notes. So I paste this here, and let me blow it up a little, I guess. So once again, we have an eigenvalue problem. We need to compute the eigenvalues of this thing, which I recommend you do in Mathematica, or you could write a little MATLAB code or a Python code. Finding the eigenvalues of a matrix is something that you basically can call a routine. And what we're interested in is we're interested in the largest eigenvalue. I want to know, is the largest eigenvalue larger than 0? Because if it is, that means one of the solutions is going to grow in time. So, so what I'm going to show you here, the plot, is the largest eigenvalue plotted as a function. So this is as a function of dy given dx equals 0.5. In other words, we've already made a choice when we made this graph, and the choice is dx equals 0.5. And what you can see is that for dy greater than, I think it's 1, the system is unstable. That means it has an instability, and the heterogeneity, the perturbation will actually grow. So that's basically what I wanted to show you about the sort of in the footsteps of Turing. What I will do in the next vignette, which I'll probably record tomorrow, is we'll do the ring of cells. So he had talked in the paper about a ring of cells. That really just means that it's a system of cells that have periodic boundary conditions. And the reason that the periodic boundary conditions is useful is it means that we can write our solution in terms of cosines. I'm not going to be able to go into the gory details of why that might be true, but we will plug in those solutions, and then that will lead us to a nice little eigenvalue, 2x2 eigenvalue problem. And we'll see that there, as you can see in this graph, this anticipates what we're going to show next, that the wavelength of the perturbation, as a function of the wavelength of the perturbation, the largest eigenvalue for sure is greater than 0. The system is unstable. It has a finite wave vector, or wavelength instability, and that's what we will try to explore. So that's kind of my introduction to some of the mathematics of the stability analysis that Turing was talking about.